the final yesterday, and it's a lot of Jordan form and Tableau that we'll talk about today, if you haven't seen it. So today, tomorrow, and I want to also take maybe Monday, do a lot of examples working with what is called cyclic Tableau, because it shows up in my multiple questions. So if you don't understand what's happening, please stop me because we have plenty of time. Like we have to finish Jordan 4 by this Friday. And next week is like extra stuff that won't show up. So I can take more time out of the extra stuff. You understand? So stop me when you don't understand, because it's a lot of material very fast. And I can stretch it, but I have to know where. Okay. So last time we talked about a generalization of the spectral theorem. So even though the spectral theorem is only true for diagonalizable, you still have this general statement for every linear map over complex, and that will be the building block for Jordan form. So let's do some examples to see how this works in practice. So we start with this map, and the first thing you want to do always is write down its matrix, because Jordan form just means a matrix representation. So that's always the first step. And by standard basis, we mean for E3, for C3. So E1, 1, 0, 0, and same thing, E2, E3. But where your scalar field are the complex numbers. All right, so right. So can someone tell me, maybe Zoom people or here, what should I put in the first column? Like which vector? Not the numbers, I don't find the numbers. Just which vector am I computing? The coordinates of which vector? Huh? No. Yeah, but not E1. Yeah. So T of E1 is equal to 6, 0, 0, and then 0, 0. So you just put 6 E1. So you put a 6. Yeah. Okay. What? Just look at it. So this is our matrix. Now let's find the eigenvalues. What are the eigenvalues? They're pretty easy to find. What are they? Lambda is oh, E1. No, T of E1. What is it? Yeah, so 6 and 7. And you can even guess the multiplicity. So what's the multiplicity for M6? Yeah, so if you take A of minus 6i, determinant, no, just put lambda. You will get 6 minus lambda squared and 7 minus lambda. Yeah, M7 is 1. The eigenvalues. I mean, can you guess the eigenvectors? Okay, you can. That's right. What do I say it here? Right. Yeah, let's find the eigenvectors. So yeah, one should be. How did I do it? Anyhow, so you have a minus 6I v has to equal 0, and yeah. So let's see. This matrix is 0, 3, 4, 0, 0, 2, 0, 0, 1. X, Y, Z equal to 0. And so you just multiply out and you get the following system. So you get 3y, 4z, 2y, z, 0, 0, 0. So what is V1? Yeah, anyways, he already said it. So it was 1, 0, 0. That's the free variable. Now, how do you find the generalized eigenvector? All right. So let me remind you. Any questions? 2. Oh yeah, the multiplicity, yes. So kernel of 6 is equal to, generalized eigenvector of 6 is equal to the kernel of a minus 6I to what power? Anybody? Zoom people? What's the power for? Oh yeah, Simon. So let's see. Anybody else? Just do with your hands the number. Yes, thank you. Ah, perfect. It's like with a bonobo, like in the wild. So, I'm sorry. I'm not going to run, I told you. I wish we had a way to get it back. So much faster. And this is also 3 because it was dim B. And dim B is 3. Right, but anyhow, so the point is, how do you find the next guy? So I have to give you the method for finding the next guy. And it's actually easy. So once you find V1, here we're trying to find the K6, okay? And these are all the V such that A minus 6I to the J of V is 0 for some J. Okay. So what you do is the following trick. Once you find V1, because it's in here, it's an eigenvector, so A of minus 6 V1 is 0, okay? Now you want to find the next guy. What do I call it? Something, X. So you want to find X, and you solve this equation, because if you do, what happens when you take the second power? What is it equal to? Don't yell it out, just do with your hands. What is it equal to? When you take, yeah, I saw your hands. Yeah, so if you act again, it will be V1, but this guy is 0. Right? Yeah, so it's 0. So what will J be? Oh yeah, that's what you meant. Yeah, J would be 2. Yeah. So J would be 2. That's what you meant. Yeah, so the J is 2. So X would be in K6. Okay? And you play this trick again. Once you find x, then you solve a minus 6i y equal to x. That will give you the third power. And so, okay. And there's only, this is three. Yeah, so that's how you play this game. So let's find, I have to look at the matrix. So let's find the x. Let's do it here. So I have to compute this guy. Oh, I have the matrix. Yeah. So the matrix is over here. So it's 0, 3, 4. That's kind of the easy part because you only have one matrix to work with. X, Y, Z. I know I'm not using notation. And but now you set it to 1, 0, 0, 0. And that gives you a system that I already wrote. So I'm not going to use it. So it's 3y plus 4z equal to what? Yeah. And then 2y 0, z 0. That makes no sense. Huh? What? Who cares? Oh, yeah. I'm sorry. Ah, so I made a mistake even before. Okay, thank you. Z to Z. Okay. Yeah, okay. I mean, this is still 0. It's just the way I wrote it. All right. Thank you. Yeah, it's flipped. Okay. Do it. Yeah, so z is 0, so z is dead. X is any number, and y will be minus 1/3, right? So my generalized eigenvector, which I hope I wrote. What? Oh yeah, I don't know why I wrote. I'm sorry. Okay, and then x is anything. X is a real number. Yeah. Okay. So what did I say here? Oh, we wrote it like this. Well, I know it's the same object, but I shouldn't have written this. So it's the span of, I don't know, like this. I'm sorry. So they have the same span. It's just, so it's 1, 0, 0, and then it's 1, 1/3 0. But they're basically the same span because you can kill off the first one. All right, so that's how you do it. Okay, when they ask you find me the generalized eigenvectors, that's how you build it up. Okay, is that okay? That's all there is to it. Don't get because this will be tested. I'm just telling you. Sure. Yeah. So we proved this result a long time ago that E of lambda is less than m lambda. We have this crazy block matrix. Oh, yeah, exactly. It will give you like it will be some element inside the span of this guy. Yeah. Actually, I should have said it. I'm sorry, you're right. So the reason we can stop here is exactly that we hit the maximum. Yeah, you will come back exactly the conjugation. Um, Anyhow, so what else did I want to say? Right, and then I'm not gonna. So this guy is actually just an eigenvector. You can do it here. So it was a minus 7i v equal to 0, and if you solve it, you get this guy. Okay. Is this still like only determinant? I mean, if you want me, I can. Let me see. So what is this? This is minus 1, 3, 4, 0, minus 1, 2, 0, 0, 0. X, Y, Z. Now this looks scary, but just work with the system. Whatever you like. Either you can do Gaussian row elimination, whatever you're more comfortable with. Okay, I wouldn't just, I would just write down the system, to be honest. But anyway, so you have minus y plus 2z equals 0, and then minus x 3y plus 4z equals 0. And here, like in Gaussian row elimination, what do? You want to like cancel them out. So maybe multiply by 3, right? And just add. Which way do you want? Okay, whatever. So you add it. So you have minus x plus 10z, and then what is it? It was minus 2. But I just want to isolate. So it's y2z. So you have a free variable, okay? So you have 1, 2, and 10, which is what we have. Okay, that's it. All right. If you have a question, just tell me. All right. Anyhow, so you found your generalized eigenvectors, and yeah, please don't do what I just did. Write 1 1/3. Okay, I don't know why I did this. So this is the span, okay, which is equivalent to the other one. Right? All right, so that's how you play this game. All right. So now I'm going to prove a Jordan block theorem that it's only temporary, but it's a good exercise for the real one. So we show that there exists a basis B so that you can write your linear map in blocks. Yes. And that's why it's called Jordan block theorem, where each of the AIs can be written as eigenvalue, the eigenvalue for the generalized eigenspace. And all I'm going to do on Friday is kill off everything above two spots away the diagonal. So it will be like 1, 1, and then 0. Okay, so we're almost there with the Jordan theorem. So that's the main. That's a prelude. Yeah, the Jordan theorem. We clean up the stuff. So it's a very concrete matrix. All right, let's prove it. Because I remember the proof was short. That's why I want to do it. So you already have the decomposition, and that's all we're going to need to get this representation. So, so all we have to do is study what happens at each block, meaning you form a basis of eigenvectors, generalized eigenvectors, and you study how T behaves restricted to the basis of the Jth graph. Okay. This one's a layer of features. So let me draw it here. So, for example, we're going to study TB, and we're going to study, let's say, the K lambda 1 basis, which are the first columns, which corresponds to the first matrix. Okay, question number 1. This map Sj is nilpotent. Can you tell me of what degree? Might be a little bit tricky for you. What can be at well? No. This is Sj to some power, is the zero map. So which part is it? Don't yell at us. Think about it and then what do you guys think? Okay, let me see. So, of dimension of who? Yeah, so it's definitely k less than the dimension of v. It's also less than the algebraic multiplicity. And what else? Yeah, so it would be exactly the geometric. Yeah, no, they're normal. They are the generalized. No. What? Yeah. Okay, fine. Yeah, we can say that one. Yes, no, you're right. No, you're right. I got mixed up. So, yeah, anyhow, so exactly, this would be the dimension of the space. So, k, yeah, exactly, and lambda. So, dimension of k lambda j t. Okay. So, let's see, how would you? So, it's closer to what was it Will? Yeah, it's closer to what Will said. So we proved a bunch of slides ago that the kernel, the degree of the Nilpotent map is at most the dimension of the space. But the dimension of the space here is the thing you restricted to, which is k lambda j. So if you were restricted on V, it would be dim V, but you're even restricted in a smaller space, k lambda j. Does that make sense? I mean, in this particular example, I'm not talking in general. Like if the restriction was not there, it would be dim V, it would be all this other stuff. But here you restrict it. So it's dim, yeah, exactly. So at most. Yeah, at most. Yeah, we'll do all this stuff. But my question was, this guy is nilpotent, and I should have said at most of what degree. It's exactly the dimension of the space. And we did this a couple of slides ago. Okay, so I don't know if you got this question, but if you're nilpotent, you only have 0 eigenvalues, okay? And okay, so what was the proof? So NV lambda. Oh, you know the proof? What is the proof? Yeah, tell me. Yeah, whatever. Suppose you have that, yes. Okay, then let me do it then. So take the degree of nilpotency, it's 0. And then on the other hand, this is lambda kv. But v is a non-zero eigenvector. So lambda is 0. Okay? Yeah, that's why it was the easiest question. There's nothing further. So all the eigenvalues are 0. And we proved this. We proved that there is a basis where your guy is upper triangular. Its axis is called Schur theorem. And we have the eigenvalues on the diagonal, right? But the diagonal is always 0. Okay, so we proved, we proved that there exist bases such that T of B is upper triangular, right? Remember? Okay. And it was very explicit because had lambda 1, lambda n. but all the eigenvalues of nilpotent are 0. Okay? All right. Okay, good. So now we know we're almost there. So what did we just do? We represented this map in a way that has 0 on the diagonal. But we still want to get AJ, which is the matrix for T restricted to KJ, generalized eigenspace, for some basis B, this guy. So how do I get to here? I just want to see if you understand the notation. It's one step. It's not really hard. I just want to make sure that you can put it in. How do I go from here to here? Do you know? All right, fine. So Sj is equal to T minus lambda J I restricted to K, and there's linearity in the representation. So when people write this, yeah, so you can, and you know this guy is this guy, this matrix. So let me do it on the right. So you just showed that T of minus lambda Ji is a guy with zeros, and yeah, you just move it to the right. There it is. No, this is like for Friday. We're just proving that you can write it in the following form. So the result we just proved, so this result we just got here says that you can write T in almost Jordan form. So you have these block matrices, and then but these matrices are of the form lambda with stuff. And on Friday will be lambda, ones, and stuff, and 0. Okay, that's called Jordan canonical form. So when people ask you to find the Jordan canonical form, they just ask you to find these block matrices. And we'll do examples, but I'm just saying. Hopefully have an example. So this is the same as before, and we found its matrix. We have this 6, 0, 0, 0. And yeah, we already found the decomposition of the space and the resulting matrix. Oh yeah. So this is the. Now we're going to compute TB. Right? You have TE. We'll find TB. And you get this, I mean, this you just do it by hand, just like, you know, the first are T of 100, second column is T 010, and the third column is T1021. Okay? So if you do that, you get your almost the Jordan form. Next week, I mean, on Friday, this will be a 1. Okay? Difference. And yeah, so this is the block matrix. Okay. I mean, I put these brackets here, but it's just the matrix for TB. It's just because in tests and stuff, there will be massive matrices. So I just wrote down blocks and then put them like I wrote here. And I wrote A1 is this, A2 is this, A3 is this, A4 is that. Don't write like the massive matrix that you're going to see. Don't do that. You won't have space, I told you. Yeah, okay, good. Questions, Sakura? Yeah, but it's the same span. So we can use the same, we can use, I think that's why I put 0, 1, 0 here. But yeah, exactly. So I might as well keep it proper. Yeah, thank you, Sakura. Yes. All right. All right. Oh, I'm gonna do it now. Oh, I see, I see. I'm just saying that we're building up to. So yeah, this would be the main theorem, right? The Jordan-Ford theorem. And what's the game in town is to find this basis, right? That's the hard part. And once you do that, you just plug things in to the basis, but you have to find the right basis that will give you this clean representation. So now starts a very difficult topic that you will be tested separately on it with a thing called cyclic tableau. I'm going to explain it. It's not really difficult, but you will have to know it inside out, like I have to when I wrote the final. So know it like your name. You know, if somebody asks you, oh, how many boxes in the first row? Degree of nilpotence. You know, it should be like this. You'll see. Okay. Let's start. Yeah, I will also take Monday. It is too much material. So take M to be nilpotent, and then we build the following basis. So we claim that there is some vectors in your space and numbers, so that you can form the following. They're called cycles. So each of them is a cycle. Okay, that's what it's called. And the special thing about it is that you start with the seed, it's called seed, and you act on it with this nilpotent map till you get to mi plus 1, at which point it's dead. We'll do examples. I mean, this is too abstract. But, huh? Yeah, and yeah. I mean, but well, are you saying we already have the basis? Yeah. That's right. Yeah, but right. Beautiful. Yes. So now we're proving that you can always do that. I mean, I just told you do it, but why? And this is why. Do you understand? Like n here will be like you said, it will be t lambda I, right? So each of them will be the basis for the generalized eigenspace. Like this would be for k lambda k, k lambda 1, and you put them together. So I'm building you the basis for the generalized eigenspace for each of them. Okay. So, and these are called cycles. Yeah. So that's the name of them. Well, don't you need I don't remember the definition for it. Like, did you need a billion or something? Or I don't remember. Like that you can like come back in a way. Yeah. That returns you to yeah, I don't remember. I don't really work in group theory, but it's very interesting. I mean, yeah, this is like an algebraic fantasy that so much of algebraic machinery shows up in actually useful things, like this generalized eigenvectors. So they went all the way in the final. Like, this is like their sync. All right. So the matrix of representation is, yeah, right. So we're almost there, basically. I got the ones. And then on Friday, we will just finish the punchline. Yeah, let me ask you here. So I have this map N, and I have this basis, and I evaluate. You should really follow the order, so be very careful. Don't start from V1. It's written like that on purpose. So you have to start from the very left and then move. So yeah, let me do. So what would be the first column? Which vector is it? Don't tell me now. Just which vector is it? Huh? Yeah. So it will be n of who? Yeah. Which is what? Yeah, which is 0. So that's how we get the first column. And the second column is m1 minus 1, v1, which is n m1 v1, which is the first vector. Right? Then, shall I keep doing like, so then you keep going and then eventually have n of v1, which is n of v1. So you put a 1 over here. But there's no v1, like never. You can never get n of x to equal some v1 stuff. Because that's the form of the basis. Do you understand? It doesn't cycle back necessarily. I mean, in this basis. So that's why you get the ones like this, and that's why you always have a 0 row and 0 column. That's called Jordan form. All we're going to do on Friday is put eigenvalues here. There's nothing. But the meat is here. Okay. Okay. All right. So if it's unclear, please tell me. And we'll do an example, I think, right after. Okay. Do I have an example? All right. Good. Yeah, and yeah, exactly. We will apply this to this when people said this map. Okay. All right. So let's do an example. Hopefully, it will take me most of the time because it's really the hardest stuff. All right. So you start with this Nilpotent map. Any ideas? What's the degree? Well, think about it. You have to like Zoom people. Do you know what the degree is? You can do it with your hand gesture. Just to see people how you find the point. Yeah. Huh? So well, yeah, that's beautiful. Yes, got a number from. So x4 got sent to 0, right? I mean the fourth quarter, like, so let's do it again. So we have z1, z2, z3, z4, z5, z6. You take n of that, then you get 0, z1, z2, 0, z4, and 0, right? And then you have that z1 is 0, z2 is x1, 0, z4 is 0. And then you just do it once more, and you just get 0. So degree is 3. What? Oh, 2. Sorry, it's 2, right? Or do I have to do it again? Okay, let me check. I rushed it. Let me do it carefully. Then this is W1, W2, W3, 5, 6. And then 3 is 0, right? 3 gets killed. There's no 3 here. So it's a 0 vector. And so you did it once. You did it 2 times, right? Or 3 times. Yes, yes. I don't know why I get mixed up. Okay, yeah, anyways, degrees 3. Oh yeah, there's so many stuff in this question. So I have to explain you how to get the signature. I know. So first, let me do the signature. It's a long question. So yeah, just a second. So first, I have to explain the signature. I added it here so that I explain it. So first of all, can you remind me what the flag is since K is 3, the potency? Yeah, what is the exact? Yeah, so it's the sequence of kernel T. And the signature are just the dimensions. So, and unfortunately, I don't know if there's a trick other than just brute force. So, yeah, okay, so yeah, actually I remember, you're right, it's actually brute force. So, so we have n of b equal to 0. So you have 0x1, might as well just write the system. Okay? So I have x1 is 0, x2 is 0, x4. I know. So then you have 3 free variables, okay? So kernel of n would be the span of E2, no, E3, E3, E5, and E6. So that's how we get this other stuff on top. Okay, I'll explain in a second. So that's kernel of n, and then we have to do it again. Okay, and for the square, and but the square is very easy, right? We just did it a few minutes ago. So let me just go to my just did. So who survived? Only x1 survived. Okay, only x1 survived. So that means you get x1 is 0. Okay, so the kernel of n squared is the span of E1, sorry, E2 to E6. Okay, so that's how you get the 5, and then we know the potency is 6, so everybody dies at 6. So that's your signature. Okay, so be able to find the signature. All right. Now, what's next? Let's see. Yeah, okay. Yeah. So, what's my question? So I have to give you. So I do that. Oh, table is next. All right, fine. Whatever. So we talked about that there is a choice of vectors that you can form a basis. And let me just postpone how you find the vectors till we do the proof. Okay, then you will see how we do all this stuff. And but okay, let me just see for a second. So what is kernel of right? No, it's not the kernel. So then I compute them, right? Okay. So then I wrote it the wrong way. So it's NV1, V1, and V2. Don't do that mistake. So yeah, like the ordering matters a lot. So let me clean this up. So and I will fix it on when I go. So this guy should be NV1, V1, and V2. Yeah, the ordering matters. And that's how because you want upper triangular. If you do it that way, you get lower triangle. So it doesn't really matter, but by convention, this is all convention. We want to have upper triangular. So indeed, this is the column for n of n squared v1, which is n cubed v1, which is 0. Okay, so you get the 0 column, and so on. N of n v1, which is n squared v1. So you put a 1 on the first guy, right? Okay, so right. And so this is your matrix. Good. Now, in the last few minutes, and we'll continue on Friday, is the secret tableau. So please, if you don't understand, just push me till you understand it. Okay, so let's do this very slowly. So once you find the basis, and we'll explain how you do it, you form the following table. Okay, namely, you take your first cycle, the longest one, and you put it on the first row. You take the second longest, and you put it third row, and then the smallest down there. Okay, that's what the secret tableau is. Just a way to represent your cycles in one picture. I did this in the textbook. He just writes the boxes, but that's the reasoning. That's because it's too tiny. Right. Yes. Beautiful. So this box has many properties, and you can prove many things in the final with this, especially the line. So make sure you practice this, guy, and so. But we will go through many things. So let me just I will list some properties. So number one is here's a nice notation that I use. So row one, the number of elements in row one, it's the nilpotency degree. But there's also stuff along the columns. So column one is the dimension of the kernel of n. I will explain why. Column two, dimension of kernel of n squared minus dimension of kernel of n. And then column three, dim kernel of n cubed minus dimension of kernel of n squared. Okay. So, and we have so let me finish this punchline. So we have the signature, right? 3, 5, 6, and you should be able to go between the signature and the table. So let me explain how you do it. The first guy gives you the number of columns for the first. So this is remember it was kernel of n. Remember? So this would be column one. The next guy was the kernel of n squared, right? And so to get the second column, you subtract 5 from 3. So Okay, so you get 5 minus 3, which is 2. So that's why you get 2 elements in there. And then in the next one, you do 5 minus 6. 6 minus 5, which is 1. So that's how you find the number of boxes. Yeah, I will continue. This is very trivial. So I will continue on Friday, and then on Monday, we'll do many examples, okay? Till we will get the hang of it. I have to go, but come back. No, tell me, where is it?
So each block is like 2% from the matrix.
What do you mean, how? You mean the basis or what?
No, like I still don't understand what the cycle tableau purpose exactly.
The what? The second?
Cycle tableau. Cycle tableau.
Oh, it just contains a lot of information. It contains all the information about the nilpotent map in one picture. Because it has the signature, it contains the nilpotency degree. Yeah.
Okay.
But you can prove things with it. So like people will give you like signature and then you can prove results about it.
Also, it has no relation with the matrix.
No, it does. That's how you form this. You form it out the basis vectors. Each row contains the basis vectors.
Okay.
Like